Welcome to the Explainer. We're all about breaking down big topics in just a few minutes. And today we are tackling something we do literally every single second of our lives: motion. All right, let's jump right in with a question, and it's one you probably think you know the answer to. How do we really describe motion? And I bet your first thought is something like, well, it's just going from point A to point B, right? But in physics, that's just not going to cut it. Precision is everything. To describe even a simple trip to the store in the language of physics, we need something way more specific. And what's so cool about this language is how universal it is. I mean, we're talking about a set of rules that can describe a falling apple, a speeding car, and even a planet orbiting the sun. It's like the fundamental code for all movement, everywhere.
So, in the next few minutes, we're going to learn the basics of that language. Ready? Let's dive in.
Okay, first up, the language of motion. We've got to start with the absolute building block, the one concept that everything else is built on. So here's the thing. In physics, just saying how much of something you have, well, it's often not enough. You also have to say which way. That's a vector quantity. Think of it like this. Saying you're driving 50 miles per hour is just a number, but saying you're driving 50 miles per hour north, now that's a vector. It's got magnitude, the 50, and direction, the north. All right, so let's take that idea of vectors and use it to describe something super basic about any journey: where you start and where you end up. This brings us to something called displacement, and it's a bit tricky, so check this out. Imagine you go for a long walk around your neighborhood, a big loop, and you end up right back at your front door. You might have walked a mile, but in physics, your displacement is 0. Why? Because displacement is just the straight line distance and direction from your start point to your finish point. Since you ended where you began, you haven't been displaced at all. Okay, so how fast are you changing your position? That's where velocity comes in. And this is a huge one. We use speed and velocity all the time like they're the same thing, but they're not. Speed is just a number, how fast you're going. Velocity, well, it's a vector. It's how fast you're going and in what direction. And get this, physics has a really clever, simple way to handle that direction part. We can just use a plus or a minus sign. If we say moving forward is positive, then a negative velocity just means you're moving backward along that same line. So simple, but it adds so much information. All right, section 3, the story of speed. Everything we've talked about so far is great for, steady, constant motion. But let's be real, when does that ever happen? In the real world, things are always changing. I mean, just think about driving in the city. You're hitting the gas, you're hitting the brakes, you're speeding up, you're slowing down. So how do we describe all that change? Well, the word for it is acceleration. Now, hold on, because this is where a lot of people get tripped up. We think acceleration just means speeding up, right? Pushing the gas pedal. But remember, velocity includes direction. So any change in velocity is acceleration. That means speeding up is acceleration, but slowing down is also acceleration. Even just turning a corner at a constant speed is acceleration because you're changing your direction. Wild, right? And what's really cool is we can actually see this in a graph. If you plot your position against time, a perfectly straight, sloped line means you're on cruise control, a constant velocity. But the second that line starts to curve, either up or down, that curve is the story of acceleration. It's a visual sign that your velocity is changing. Okay, so now we have the language to describe motion perfectly. Displacement, velocity, acceleration, we've got it. But this leads to the next, maybe the biggest question. Why? Why does motion change at all? And the answer, thanks to Isaac Newton, is beautifully simple. Basically, objects are kind of lazy. They want to keep doing whatever they're already doing. To change that, to cause an acceleration, you have to give it a push or a pull. And that push or pull, that's what we call a force. Forces are the reason for any change in motion. And once you know what to look for, you realize forces are absolutely everywhere. I mean, right now, the force of gravity is pulling you down into your chair. And the chair, it's pushing back up on you with a reaction force. Without it, you'd fall right through the floor. Okay, let's zoom in on one specific force now. It's one that impacts almost everything that moves on Earth, but a lot of the time we totally forget it's even there. Let's talk about friction.
You've totally felt this before, right? You try to push a heavy box or a piece of furniture, and it takes this huge grunt to get it to move. But once it starts sliding, it's a little bit easier to keep it going. So why is that? The secret is that there are actually two kinds of friction at play.
So here's the deal. When that box is just sitting there, you're fighting what's called static friction. You can think of it like a really stubborn glue holding it to the floor. It's strong. But the moment you overcome it and the box starts to move, the friction changes. Now you're dealing with dynamic friction, which is weaker. And that's it. That's why it's easier to keep it sliding than to get it started. And of course, how much friction you have depends on the surfaces themselves, how rough or grippy they are. We measure this with something called the coefficient of friction. It's just a number that tells you how rough the interaction is. And that explains why pushing a box on slick ice is way, way easier than pushing it across a thick, shaggy carpet. The coefficients are just completely different. So there you have it. From displacement and velocity, all the way to the forces like friction that cause acceleration, you now have the basic vocabulary. You've got the tools to read the story of motion that's happening all around you all the time. And I'll leave you with a final thought to chew on. We've just talked about the rules of motion here on Earth. But what happens when you change the rules? What happens in the near-zero friction of space? If you push something, what happens when there's nothing there to slow it down, ever? Thinking about that is how these basic concepts become the key to understanding the entire universe. Thanks for joining us on The Explainer.